In the last lecture, we have discussed about the extremization of a function of a single, two and many variables where there were no restriction. Such unconditional variation mm, oc- occurs sometimes in nature, but mostly it is found that the conditional variation of a function is um, very frequently occurs in physical problems. Say for example, we have a function of two variables. This is the conditional variation. So today's topic is conditional extremization of a function. Firstly, you consider a function of two variables. A function of two variables. With one constraint. Let us consider first describe what do you mean by constraint. Say a particle is moving in a plane. So for two-dimensional motion is concerned, the particle is moving freely. Now, if one puts a restriction that the particle has to move along a straight line, then this is a condition. Some other constraint, some other type of constraint may be like that the particle is compelled to move on the circumference of a curve, say for example a square, say for example a sphere. Then the particle will no more have 2 degrees of freedom, or it is not required to express the position of the particle in terms of two variables x and y, two coordinates. Rather, one condition is sufficient, because if you specify x, then the other y will be specified by the condition imposed. Our problem is to extremize the function f subjected to some constraints. As the first example, we consider a function f of two variables x and y, on which there is a constraint g. The function is f of xy. Aim is to extremize this. Constraint is g of xy is some constant. Had there been no constraint, we could set the first derivatives to 0 to get the stationary points, or the points at which the function has an extremum value, and then we go for the analysis of nature of extremization. Here we restrict ourselves to find the values of x0 and y0. So for extremum value, we write df is equal to del f del x dx plus del f del y dy. At the stationary point, this is 0. So this is df at stationary point. The stationary point again will be represented by x0, y0, which is denoted by this. So at the stationary point, at stationary points, we have this is equal to 0, that is del f del x at 0 times dx plus del f del y at 0 times dy is equal to 0. In the case of unconditional variation, we set this equal to 0 simultaneously this equal to 0, because and in that case x and y were independent variable, and both dx and dy can have any value irrespective of the other. So to satisfy this condition, we must have this equal to 0 together with this equal to 0. But in this case, x, y are related by this condition. So while we write the equation of constant in the differential form as dg is equal to dg del x dx plus del g del y dy. This is equal to 0 because it is equal to constant. Note that this condition is equal to 0 only at stationary points, and this is at all points. At all points, even stationary point is also included in this. So one way of solving the problem is to solve this g function as x, to get x as a function of y and c, and we substitute the value of x into this, so that f will be effectively a function of y only, and we perform the extremization of f, which is a function of y. But this functional form may be very complicated, or in some cases where there are more than one variables involved, such elimination may not be trivial. So what we are looking for? We are looking for a systematic prescription for the extremization of a function f subjected to some condition. A condition or conditions, how to solve it. As per Lagrange, he introduced some multipliers, and as per Lagrange he defined a function h which is f plus lambda g if there is only one condition, which leads to dh is equal to df plus lambda dg. You note that dg is 0 at all points and df is 0 only at stationary points. So this is equal to 0 at stationary points. Points provided lambda is a finite quantity. In which case, we demand that both x and y are independent of each other, so that this becomes del f del x plus lambda del g del x dx plus del f del y plus lambda del g del y dy is equal to, this is equal to 0 at the stationary points. We say that any lambda, finite lambda, will solve our purpose. We choose these equations to determine lambda. So to be specific, this is at 0, this is at 0. We set it to 0 to get lambda. So first equation we set to 0 to get lambda. Then we yet to know x0 and y0. This gives us an equation involving x0 and y0. But we have one variable, one equation and two variables yet to be known. But there is one more equation. This equation is also valid at x0, y0. So we will have this and these three equations and three unknowns, x0, y0 and lambda. So this is a very standard prescription which can be applied to more than one variable subjected to one or more constants. So the prescription is that we consider the function and we consider the constant. We take the differential of both and multiply the differential of the constant by multiplier lambda for Lagrange's undetermined multiplier, whose name will be clear soon, and set the total differential to 0 at the stationary points. Here we forcibly set lambda to have such a value so that it makes 0. So we will have a function of a single variable x, which is say obviously equal to 0 because it has to be 0, and 3 are to know 3 unknowns. We use this is an equation equal to 0, this is 0, and this is equal to 0. To make the things clear, we take a simple example. Say the temperature distribution, and we consider the example like a temperature distribution in xy plane is given by x square minus xy plus y square. This gives us the temperature at any point in xy plane. Our aim is to find f max such on a circle x square plus y square is equal to 5 square. So our condition of constraint is g of xy is equal to x square plus y square minus 25 is equal to 0. Now what to do? As per Lagrange's prescription, since we have one constant, one undetermined multiplier will be required, so we calculate dh is equal to df plus lambda dg. This is equal to, if we differentiate it with respect to x, 2x minus y plus twice lambda x dx plus, if we differentiate it with respect to y, this is 2y minus x plus 2 lambda y dy is equal to, we set it equal to. So at the stationary points we have 2x minus y plus 2 lambda x is equal to 0 and 2y minus x plus 2 lambda y is equal to 0. This equation gives minus 2 lambda xy is equal to 2x square minus xy, and this equation gives minus 2 lambda xy is equal to 2y square minus xy. What we have done? We have multiplied this equation by x and y. Sorry, we have multiplied this equation by y, so we get 2xy minus y square, and when we multiply this equation by x, we get 2xy minus x square. When we equate these two, we get x square is equal to y square, which gives x0 is equal to plus minus y0 at the stationary points. Now, what is the value of x0, y0? We have only come to the conclusion this is the relation. So we put this value into this equation so that x0 square plus y0 square is equal to 5 square, or twice x0 square is equal to 5, or x0 is equal to plus minus 5 root 2. So the stationary points are plus minus 5 root 2, 1 plus minus 1. So there are 4 points on the circle at which the function, if the function f may have either maximum, may have a maxima or a minima. To get the maximum and minima, we have to go for second derivative, but at present we are not going to this. We are restricting ourselves to the determination of x0 y0, that is, we want to locate the stationary points only. So these are the 4 stationary points for the function thus subjected to this condition. If we can just change the condition, then the function will have extremum values at some other points. Now, if we extend the theory to more than one variable, and which may in general be imposed more than one constraint. So we consider a function of n variables which are subjected to k number of constraints, and obviously the number of k must be less than n. So we have a function of n variables. So we have function of x where x vector is, as we have done in the previous class, x1, x2 up to xn, and there are gi conditions, where I ranges from 1 to up to k with k less than n. So for example, if we have n is equal to 6 and k is equal to 2, then we will have n minus k variables, in this case n minus k independent variables. Variables are there. So as per Lagrange prescription, here we construct h is equal to f plus lambda 1 g1 plus lambda 2 g2 right up to lambda k gk. That is, this is f plus summation over I is equal to 1 to k lambda I gi. Then we set we calculate dh, which is del f del x1. If we write it in longhand, del f del x1 plus lambda 1 del g1 del x1 plus lambda k del gk del x1 multiplied by dx1 plus del f del x2 lambda 2 del g1 del x2 lambda k del gk del x2 times dx2 del f del xn plus lambda 1 del g1 del xn lambda k del gk del xn dxn. So there are k number of undetermined multipliers has been introduced, and there are, so K conditions are to be necessary to determine this K number of multipliers. We use this last K equation to determine lambda, and first n minus K equation are used as first n minus x, that is dx1 dx2 up to dx n minus k are treated as independent, which can be varied at will. So this is equal to 0. So we write del f del xj plus summation over I lambda I del gi del xj. This is equal to 0 for j is equal to 1 to n minus k, which are independent variables, which are treated as independent variables. And rest this equation del f del xj plus lambda I is equal to 1 to k. This is 1 to k. Lambda I del gi del xj, they are set equal to 0, with j ranging from n minus k plus 1 to n for the determination of lambda. Of lambda i's, which are k in number. So we see that the condition is same for all j is equal to 1 to n. Now the problem is, let me summarize the problem. There are n x values to be determined together with k number of multipliers. So x values are n in number and lambda values are k in number. So in together we have n plus k unknowns. There are n conditions and there are k conditions of constraints which are also valid at the stationary points. So this n variations together with k equation of constraints allows us to determine n plus k constraints. Let me apply the theory to few simple problems. Consider a particle moving in a three-dimensional cuboidal box, quantum particle, cuboidal box. Say this is a free particle. So we know that the energy expression, a quantum particle in 3D cuboidal box. Now the energy, we know that the energy is E nx ny and z is equal to pi square h line square by 2m nx square where x square is the length of the box along x-axis, and y square plus mz square by z square, where y is the length of the box along y-axis and z. So the ground state energy Eg is equal to a 1 plus x square 1 plus y square 1 plus z square, where we set a is equal to y square h line square by 2m, where m is the mass of the particle, and the volume of the box is xyz, we say it is a constant is equal to, it is a constant c. So our problem is to minimize eg subjected to this constraint. So in is to minimize eg subjected to b minus c is equal to 0. So this is a three variable problem, and one condition has been imposed, so two variables can be treated as independent. And to find out the extremum value or stationary value, we need to know x0, y0, z0 together with one multiplier. So we set this as deg plus lambda, and this is dv. We call v is equal, this is equal to 0, subjected to v is equal to, then this condition becomes subjected to condition v is equal to 0. It's then lambda dv, which is equal to minus 2a x cube from the, this is the del eg. Note that del eg del x is equal to minus 2 upon x cube, and del v del x is equal to yz. So this is lambda times yz dx y cube lambda zx dy So there are three unknowns are to be determined. There are four unknowns. These are the three conditions, and this is the fourth condition. We set each one of them to 0 as per Lagrange's prescription. So we get minus 2a x cube plus lambda yz is equal to 0, which gives us lambda xyz is equal to 2a by x square. My second condition gives lambda zx is equal to 0, which gives you lambda xyz is equal to 2a by y square. And the third condition is 2a by z cube plus lambda xy is equal to 0, which gives you lambda xyz is equal to 2a by z square. If we solve this, this gives you x is equal to y. Since x and y can never be negative, they are the length of the box, and this gives you y is equal to z. So we get x0 is equal to y0 is equal to z0. That is, to have the minimum energy, the box must be in the form of a cube. Now, it is not sure whether this is an extreme minimum value or maximum value. For that, we are to perform second variation, which we are not doing. But actual calculation shows that it is a minimum value of Eg. We consider another example. We consider a cuboidal hollow box. A cuboidal hollow box with one side open. And the box has a fixed volume. Our aim is to find out the shape so that the surface area is an extremum one. With one side open. So let the box have let the box have dimensions x, y, z. So the volume of the box is x, y, z. Say this is 32 meter cube. It is the constant. Our aim is to extremize the surface area. To extremize. Oh, one thing. In the last two examples, we have found the stationary value, but we do not bother to calculate lambda. So lambda was introduced to facilitate our calculation, but actually we are not after getting the value of lambda, although it can be obtained, because the problem that was given at the beginning, there were no rule of lambda. Lambda was introduced to facilitate calculation, and in general we do not require to find lambda. That's why it is called undetermined multiplier. Now we set the final function as h is equal to s plus lambda v, and then bh is equal to 0 leads to del s del x. So this is del s del x plus lambda del v del x is equal to 0 is equal to y plus 2z plus lambda yz is equal to 0, del s del y plus lambda del v del y is equal to 0, which gives x plus 2z plus lambda zx is equal to 0, del s del z plus lambda del v del z is equal to 0, which gives us del z. So 2y plus 2x plus lambda xy is equal to 0. If we multiply it by x, this gives you minus lambda xyz is equal to xy plus 2zx. If we multiply this by y, we get minus lambda xyz is equal to xy plus twice zy. And if we multiply the last one by z, we get minus lambda xyz is equal to 2yz plus 2zx. If we equate these two equations, we get that x0 is equal to y0. If we equate these two equations, these two zy goes and we get y0 is equal to twice z0. So we get the condition that for extremum value we must have x0, y0 is equal to 2z0. Say this is equal to a. We put it in this equation of constraint. So we have a by 2 is equal to 32, which gives a is equal to 4. So the side of the box is x0 is equal to 4 meter, y0 is equal to 4 meter, and z0 is equal to 2 meter. So this is the optimum side of extremum value of S. Note two things. One is we have not obtained lambda from here, although we can find out lambda. If we put the value of x0, y0 and z0 in this equation, we can find lambda, or indeed we can find lambda, but we are not after it. That's why lambda is called undetermined multiplier. Second, see, before going to the calculation, it may seem that the optimum size will be a cube, but no, it's not a cube. It has a special form that x0, y0 are equal and z0 are not. And this note that the open surface is a z is equal to constant surface that we have taken. So with this introduction to the extremization of a function, we shall in the next class consider the extremization of a function subjected to some condition, and we shall again use the Lagrange's method of undetermined multiplier. It will be found that when we use this constant variation of functions to Lagrangian mechanics, to be specific, when we use the Lagrangian mechanics to conservative non-holonomic system, in that case we shall find that the lambda has a special significance. This lambda, in that case, lambda gives the force of constraints, and in that case we may find lambda to know the force of constraints.